All right, you guys, I'm going to try to keep this brief, but I just don't know how I'm going to. I kind of put off this lecture or recording this lecture. I've been like procrastinating all afternoon and evening because I just had this terrible feeling that I'm going to do it and it's going to be too long. Here I am already with too long of an intro, and then you guys are going to freak out when you see how long it is. Whatever, you can like do what Anthony does and play it at like triple speed so I sound like a chipmunk. No, don't do that. But what I would do is I would sort of listen to me explain a portion of it and then pause and take the notes. Okay? I think that's how you should do it. I don't think you should like pause after every, sentence or definition. Okay. So now that I've already set myself back by a minute, let's talk about the quantum mechanical model of the atom. All right. So we left off talking about Bohr yesterday and about electrons having energy and existing in these set circular orbits. Well, along comes a guy named Heisenberg. And what Heisenberg did is he mathematically related the uncertainty or the error in both the momentum and the location of an electron. And it turns out that when he actually measured the uncertainty in position or location, it turns out that the plus minus or the uncertainty of that position was bigger than the radius of the atom. So like if the uncertainty in position is bigger than the size of the thing itself, then there's no way that we can say for certain where an electron is located in that atom. How close to the nucleus is it? How far away from the nucleus is it? What energy level is it in? Like, there's just no way. The analogy that I often make for this is like, it would be like you guys saying, oh, I know for sure that Mrs. Rivera is in room 325, plus or minus 3 miles. Well, like, if your plus minus on my location is 3 miles, which is bigger than the size of the campus itself, there's no way that you know what room I'm in. So that's basically what happened when Heisenberg did this math. So essentially, it's impossible to know both the speed and position at the same time. So what does that mean? That means that we can no longer use Bohr's model of these set circular orbits, right? We don't know for sure that the electrons are in those set circular orbits. And instead, we have to base the electron's location on the probability of finding it in a particular place. Okay, mathematical probability. So there was a bunch of fancy math that happened to lead us from Bohr's model. Bohr's model was called just the quantum model. That was Bohr, right? Giving electrons quantized amounts of energy, to the quantum mechanical model of the atom, talking about the motion of the electron and the probability of finding them in a particular place. So the two guys that were key in this was a guy by the name of de Broglie. He was the one that determined that electrons have wave-like properties. And there's an equation called the de Broglie wave equation. Again, we're not going to get into all of the math. I mean, the de Broglie wave equation is not complicated. You can basically just calculate the wavelength of a particular electron. It's in your textbook, but we don't need to get into it here. And the other guy who was really important in coming up with the quantum mechanical model was a guy by the name of Schrodinger. And he is the one who actually came up with what we call the wave function. Again, you guys will take a bunch of crazy calculus and particle physics and whatnot. The wave function is given as the variable psi, and Schrodinger actually graphed the square of the wave function. We don't have to get into all of the math. Just know that when Schrodinger graphed this, which is essentially graphing all of the possible positions of an electron, certain shapes started to appear. So I want you to start thinking three-dimensionally, you guys. So ignore these shapes here off to the side for a second, although I know you already know what they are. And just look at like my little three-dimensional graph, my x, y, and my, oh my God, that was supposed to be a straight line. Okay, my x, y, and z axis. So Schrodinger takes, the first electron in hydrogen, and he starts graphing the square of the wave function. And every time there's a mathematical point or place on this three-dimensional axis that the electron could be located, he made a point, right? So sometimes the electron was located there. Oh, by the way, the origin would be the nucleus. And sometimes the electron is there, and sometimes it's there, and sometimes it's there, sometimes it's there. And so he just plotted all of the possible points and places where that first electron, well, only electron in the case of hydrogen, is located. And what you guys might start to see taking shape here is like a sphere. And, occasionally the electrons were out here as well. But the densest part of the sphere was located like right around there. Oh, good job, Amanda, drawing a circle. So this is the place where that hydrogen electron was found 90% of the time. And so we say, all right, well, that's probably the place where hydrogen's one electron is most likely to be located. These shapes that started to appear when we graph the square of the wave function are called atomic orbitals. So instead of Bohr's, I realize I'm like underlining everything, sorry. Instead of Bohr's set circular orbits, now these three-dimensional areas of probability are called orbitals. All right, so these are three-dimensional areas of probability where we have a 90% chance of finding the electron that we are graphing the wave function of. These areas of probability have specific shapes. So as you will notice off here to the left, there are spherical shapes. We call those s orbitals. There are these dumbbell shapes. Those are what we call the p orbitals. How do you spell dumbbell? Do you think there's two B's? I don't know. That looks right to me. And I'm going to go kind of fast here, you guys, right? Because you've heard this lecture before. This should be a review for almost all of you. All right, so we have spherical shapes. We have dumbbell shapes. These dumbbell shape orbitals are called p orbitals. There is the px orbital, the pz orbital, and the py orbital. You might see me label these axes differently, like x, y, z. It doesn't matter in three-dimensional space. And so, the p orbitals are all dumbbells. It's just that one lies along the x, one lies along the z, and one lies along the y. So we've talked about spheres, we've talked about dumbbells. These d orbitals I call butterflies shaped. They're not all butterfly shaped. Do you guys see this one here in the middle, right? Where it's just on the z with like a donut hole around it. It's kind of a fun shape. And then lastly are the f orbitals, and they're all sorts of crazy shapes. Okay. Besides having certain shapes, orbitals also have specific sizes. So going back to my crazy little diagram here, when Schrodinger went and graphed the second electron, which would be in a helium atom, we got another area of density that was slightly larger. Ignore me while I draw all of these little dots. Slightly larger than the 1s orbital. It was still a spherical shape, but the probability density area was now wider ranging. It was now larger than that first orbital was. So these orbitals can all get bigger in size. The other thing you should know about these orbitals is they can, they have certain orientations. Like what axis do they lie along, right? We already kind of talked about that, but I didn't write it down over here. That's where I'm talking about like the px, the py, the pz, the dxy, that butterfly shape lying in between these two planes. And then lastly, these orbitals can hold 2 electrons maximum. And in order to hold 2 electrons, 2 negatively charged things that are repelling one another, they have to have opposite spins. One has to have a clockwise spin and one has to have a counterclockwise spin in order to avoid repelling each other out of this area around the nucleus. So if that's the case, right, if this spherical orbital can hold 2 electrons, that's the maximum that we can have in the what we would call the s sublevel. Now the p's can hold 2 each, right? So I can put 2 electrons here, 2 electrons here, and 2 electrons there. So the p sublevel can actually hold a maximum of 6 electrons. The d, with their 5 different orientations, can hold a maximum of 10 electrons. And of course, the f orbitals can hold 14 electrons. We call those a sublevel. Okay, so like all of the orbitals within, all of the orbitals making up this p, we call a sublevel. So the px, the py, and the pz are a sublevel. Okay, we'll get into all of this vocabulary a little bit more once we actually write some of these electron configurations. I just want you to start thinking about what did these wave functions sort of create, right? And they created these atomic orbitals, which are now the houses and the homes that we're putting these electrons. Now they're all separated out here, but actually these things lie on top of one another. Okay, so like you guys can see, I drew the 1s, and then on top of that is the 2s, and then on top of that, maybe I'll change color. Maybe I'll go to yellow, right? Because we have the yellow P's here. So the P's, oh, you can't see the yellow. Just kidding. I'll do red. Okay, so the P's here would be the 2px, the 2pz, and the 2py. And then there's another 3s orbital on top of that. You can see it's getting bigger. And then the 3 p's on top of that. Now my p orbitals are getting bigger. This is crazy, right? Like, you know, yes, this looks nuts, but it actually works as a really good model for us. But we don't draw it all on top of each other like that. Like that model that I just drew right there, that doesn't work so well. But the electron configurations that we're going to write later are really good representations of this big 3-dimensional mess that I just drew. Okay, now here is something new that we didn't talk about last year. And that is taking like a sort of like a more detailed look at all of those dots I was drawing, right? All of those possible points and locations of finding possibilities or probabilities, I should say, of finding an electron in a particular location. And so one of the ways in which we do that is by looking at something called radial probability distributions. Now this sounds all big and scary, but it's really not. Okay, radial probability distributions. These are just graphs that show us the most probable location of finding an electron with respect to distance from the nucleus. So like how likely are we to find the electron at this distance from the nucleus versus that distance from the nucleus? So on my y-axis here is the probability. And on my x-axis here is distance from the nucleus. So if we look at the probability of finding an electron in the 1s orbital, okay, the most probable location for that electron, the peak of this graph, is at about 0.5 angstroms from the nucleus. Angstrom is a new unit of measure for you, probably. An angstrom is 1 × 10 to the negative 10th meters. I actually think I talked about this yesterday when we were talking about nano, that nano is 1 × 10 to the negative 9th meters, and angstrom is a power of 10 off from that, 1 × 10 to the negative 10th meters. You're like, well, why do we have another unit? Well, it's about the radius of a hydrogen atom. So it's a useful unit of measure for us because it kind of relates pretty closely to the sizes of atoms. Okay, so the most likely location for this 1s electron is 0.5 angstrom from the nucleus. Now notice here at 0 in the nucleus, there is 0 probability of finding the electron there. Like there's no chance that you're going to find the electron in the nucleus. That is what we call a node. And that's where you have no chance of finding the electron. And you'll notice we'll see a couple of nodes here when we start talking about the other orbitals. Okay, so in other words, this is just telling me the size of the 1s orbital. You know, the most likely location for finding the electron in the 1s is about 0.5 angstrom from the nucleus. If we were to graph the probability of finding an electron in a 2s electron, like where would that 2s electron be? Do you guys see how there's like a little bit of a chance? Like there's a little bit of a probability of finding the 2s electron in the 1s orbital. Like it's possible. It's not super possible, but it is possible. In other words, on this layered diagram that I was showing you guys, when I'm graphing the locations of the 2s electron, it could be in the 1s. It's most likely to be farther out from that 1s. Maybe I should like redraw this crazy thing. Oh my God, my cats are like scratching. They're trying to come in the office. All I want is food. All right, so like here's my 1s. And then here is the 2s. Is there a chance with this overlap situation that we have that the 2s electron is in here in this 1s area? Yeah, it's possible, but it's more likely that it's out here in this darker shaded area that I just drew. Okay? Now, what's really crazy is there's a node between these two things. Remember I said a node is a chance where you're never going to find the electron? This red area, this sort of borderland between the 1s and the 2s, there's no chance of finding the electron there, which is crazy because that means that electrons somehow can be inside that border area and can sometimes be outside that border area, but never in that border area. You guys, don't ask me to explain. It's like, that whole thing about like, is the cat alive or dead? It's crazy. It's crazy. Quantum mechanics is crazy. Have fun in physics. Anyway, where's that node I was talking about? Let's look at our graph here. So my 2s is this green line, right? So there's a chance that that electron is in there, but there's another node between the 1s and the 2s area where I'm not going to find that electron. Most likely place to find it is around 3 angstrom from the nucleus. In other words, the 2s is a bigger orbital than the 1s. There's like a greater range of places to find the electron when it's a 2s electron. The whole explanation I just gave is also true for the 3s electron. Is there a chance that the 3s electron is in that 1s area? Yep. Is there a chance that it's in that 2s area? Yep. Where's the most likely place? In this larger area outside. Okay, so do you want me to draw the crazy drawing again? You're like, no, please stop drawing it. That's why this lecture is going to be so long. All right, so like there's our 1s orbital. There's I totally forgot I have a diagram of this down below. There's our 2s orbital. And then our 3s orbital is even bigger, okay? And there are those nodes in between where we're never going to find the electron. So there's another node right there. So how does the electron do it? I don't know. Here's what I'm talking about with these nodes, you guys. Aha, isn't that pretty? So like here are all of the places where we can find a 1s electron. There's that 1s electron. Here are all the places we can find that 2s electron and then the 3s electrons. Okay, and these white areas represent those nodes where the electrons cannot be. There's also a node at the nucleus, obviously. Okay, so we need to start putting the electrons into all of these homes. So like I have just showed you that there are these orbitals that, layer on top of one another and get, have different shapes and they get bigger and bigger. And so like these are houses for electrons. And we put the electrons in these houses according to a set of 3 simple rules. Now, you might be stressing out a little bit because you're like, oh my God, last year I had to memorize. Like first was the 1s, and next was the 2s, and next was the 2p, and next was the 3s, and next was the 3p, and next was the 4s, and then the 3d, blah, 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 blah. Remember this fill sequence? You don't have to memorize it, okay? There's a cheat method for knowing this fill sequence, and it's by reading it off the periodic table. But before we even look at that cheat method for remembering the fill sequence, let's just put some electrons in houses. And let's just look at the fill sequence. Okay, so I told you that the first orbital is the 1s orbital. So if I wanted to represent hydrogen's 1 electron, okay, so like hydrogen has 1 electron. Where is hydrogen's 1 electron going to go? Well, it's going to go in this 1s orbital, and we draw that electron, remember, as an up spin arrow. I draw half arrows. Well, why is hydrogen's 1 electron going to go in that 1s orbital? Because of the Aufbau rule. The Aufbau rule, or Aufbau principle, states that, well, this is how I state it. Electrons are lazy. That's not like the real rule. The real rule is that electrons fill from lowest energy level, lowest energy orbital, to higher energy orbitals. And it's not because they're lazy. It's because they are attracted to the protons in the nucleus. So it would take more energy for them to go up into these higher orbitals. They're more stable down here in these lower orbitals. I just had a terrible feeling that I've been like talking for half an hour and not recording, or something went wrong. So I'm going to check. Okay, looks like everything's okay. Whew, that would be bad. All right. So that's why that hydrogen electron is right there. Now, how do we represent this? I just represented it with like a diagram with an arrow. I can also represent it by writing 1s1. In other words, first energy level, S-shaped orbital, 1 electron in it. But what if I had helium? Helium has 2 electrons. So where's that second electron going to go? Remember, the 1s orbital can hold 2 electrons. So there, helium's second electron will lie. Remember, they have to have opposite spins so that they don't repel each other right out of that orbital. We call this the Pauli exclusion principle. Electrons must have opposite spins in order to reduce repulsions. Oh, I forgot the word to. In order to reduce repulsions and occupy the same orbital. All right, we can represent this as 1s2. First energy level, S-shaped orbital, housing 2 electrons in it. What about, you know what, you guys, we're going to jump ahead. You guys know how to do this. We've done this before. Let's jump ahead to 1, 2, 3, 4, 5, 6. Let's go to 7. Let's go to nitrogen. 7 electrons to put in their houses. Nitrogen has 7 electrons. The first 2 are going to go in the 1s. 1, 2. Next 2 electrons, going to go in the 2s, right? We go low to high energy. So 1, 2, 3, 4. I have 3 electrons left. They're going to go into the 2p sublevel. 1, 2, 3. So that's 7 in total. 1, 2, 3, 4, 5, 6, 7. Notice how I spread them out within that sublevel. This is called the Hund rule. And I call this the empty bus seat rule. Well, I did not coin this term. It's like every chemistry teacher everywhere calls it this. It's like if you're getting on the bus and somebody sits next to you when there's an open seat right behind you, it's like, dude, awkward, right? So it doesn't take any more energy. See how all of these P orientations, the PX, the PY, the PZ, see how they're all the same amount of energy, right? Because we've got increasing energy here on our y-axis. So it doesn't take any more energy to spread these electrons out. So there won't be any repulsions. They will spread out within a sublevel before pairing up. Electrons spread out within a sublevel before pairing. Okay, so how do I represent this? This is my diagram. Let's write my configuration. 1s2, 2s2, 2p3. My 1s has 2 electrons in it, my 2s has 2 electrons in it, and my 2p has 1, 2, 3 electrons in it. Okay? This right here that I just wrote, you guys, is called the longhand electron configuration. And it's important that we recognize what each of these different things is telling us. Okay? So these numbers out in front, the 1, the 2, and the 2. These coefficients are representing the principal energy level that electron is in. It's also telling us, essentially, the size of the orbital. Okay? The letters, the S, the P, and if we were going on to D's and F's, these letters are representing the shape of the orbital. And lastly, these superscripts are telling us the number of electrons in the sublevel. Okay, now let's backtrack to how I know that this is the fill sequence, right? So like if we look up here, it gets a little confusing because it's like 1s, 2s, 2p, 3s, 3p, 4s, and then 3d. You're like, what? Why if the 3d is like closer to the nucleus than the 4s? So why is it higher energy than the 4s? That seems weird. It has to do with this combination of not just size of the orbital, but also shape of the orbital. The shape of this 3D orbital actually gives it slightly higher energy than the 4s. So it's a little bit weird that you would fill the 4s before filling the 3D. In fact, maybe let's, well, we can do it later. I was going to say, let's do a fill sequence for something in the 3D, but we'll do a nice long one here after we talk about how we know this fill sequence. So for those of you that didn't use this method last year, I mean, if you had me, you did, so no excuses. Down here, I want you guys to label your periodic table. You know, if you've got a plain periodic table that you can put some Sharpie on or whatnot, label the S, P, D, and F blocks. So what you'll notice here is that groups 1 and 2 plus helium, these are considered S block elements. Then your 6 element across, and hello, by the way, you guys, right? S orbitals can hold 2 electrons. Look at this. 1, oops, maybe I should use green. S orbitals can hold, I'll use black. S orbitals can hold 2 electrons. So 1, 2. Look, 1, 2, 1, 2. Get it? Right? S orbitals can hold 2 electrons. P orbitals can hold 6, right? Because remember the 3 different shapes, 2 electrons apiece. 1, 2, 3, 4, 5, 6. Voila. These are our P block elements. D's, if you'll just see on your periodic table, D's are 10 across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across. And your Fs are 14 across. And of course, remember the 5D and 6D. Why are they over here? They should really be over here. The lanthanum and actinium. I don't like that they put them over there. Some people fill them before, some people fill them after. It's not important. We're not going to do any crazy F block stuff. But anyway, your Fs are 14 across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So when we're filling up through the 5, the 4F and the 5D, you can either put your 5Ds, because the first 5D actually fills before the first 4F does. But if you have a full 5D, you could put your 4Fs first and then all of your 5Ds together, instead of saying like 5D1, 4F 14, 5D6. Like, you wouldn't do that. You could either say 5D7, 4F 14, or you could have said 4F14, 5D7. So, don't worry about it. The AP exam is not going to take you down through all of these gigantic elements. But anyway, my point in showing this to you guys is that you just read your periodic table left to right, top to bottom. So like, here's my first period, second, third, fourth, fifth, sixth, seventh. First orbital is the 1s. The next one we come across is the 2s. Keep going. The next we come across is the 2p, and the 3s, and then the 3p, and the 4s, and then, the D block goes down by 1. So you just have to remember the D energy level down by 1 from the period that it's in. Okay, so this is the 3D, not the 4D, and then back up to the 4p. The energy levels for the F orbitals actually go down by 2 n minus 2. And so now you don't have to memorize the fill sequence. You can just read it off the periodic table. All right, so let's do that, shall we? We're almost done. You guys are doing a good job, I think. I don't know. Maybe you're listening to me in like quadruple time and you have no idea what's going on. Who knows? Okay, let's do a longhand configuration. Let me pull up my periodic table. Let's do bromine. 35 electrons. Here we go. So we're going to do the longhand configuration for bromine. 1s, 2. 2s, 2, right? We just keep filling up these orbitals. 2p, 6. 3s, 2. 3p, 6. 4s, 2. 3d, 10. 4p. 1, 2, 3, 4, 5. Voila. This right here, you guys, is your longhand electron configuration. Let's review. Remember, these coefficients out in front are how big the orbitals are. That's your principal energy level. The sublevels would be the shapes of the orbitals. So like this 3s right here, that is a sublevel. This 3p, including all of the p's, the px, the py, the pz, that is a sublevel. And this is how many electrons are in each of those sublevels. We can also represent this with an orbital diagram, just like we were showing up above here, like these boxes with the arrows in them. But instead of going up, we can just go across. Okay, so we draw one box for our 1s, because it can hold 2 electrons, one box for our 2s, 3 for our p's to represent the x, the y, and the z, 1 for my s, 3 for my p's. Notice how I leave these nice little spaces in between. All right, for my d's, remember I have 5 orientations, 1, 2, 3, 4, 5, 3d, and then 4p, 1, 2, 3. Okie dokie. Let's fill these up with electrons. Now you can really speed me up. Notice how I spread these guys out before pairing them up. It's just a good habit. Up, down. Up, down. You guys, this year, we are going to use this model to explain bonding, and it's going to be so freaking cool. You're going to love it. It's called hybridization. How many electrons in here? 5. 1, 2, 3, 4, 5. This is my orbital diagram. Okay, so again, let's talk about principal energy level versus sublevel. Okay, so what color did I do for principal energy level up here? Let's be consistent. Oh, like the purpley color. Okay, so this, oh, was it this one? I don't know, we'll find out. Okay, so principal energy levels. Energy level 1. Check this out. Energy level 2 includes all of those electrons. You know what? I don't like how I did that. Okay. Oh, now I just erased an electron. Okay. I'm going to put a box around each energy level. So there are 2 electrons in the first energy level. Look, there are 8 electrons in the second energy level. Don't forget this 3D over here too. Okay, so maybe I'll put like a double box around the third energy level so we can see it, that it's all partnered together. Okay, look at that. There are 18 electrons in the third energy level. And then the 4s and the 4p. They're their own little energy level too. I should have done different colors. This is a disaster. I really hate what I just did there, you guys. Let's do different colors. Do you hate me? You're like, I want this lecture to be over. Okay, now let's just do random colors so that we can see the different energy levels. You know, you guys, I'm just trying to be clear. Sometimes it takes a few tries. There we go. I like this much better. All right, so in all those different colors, you guys, all those different colors represent the principal energy levels. Inside each box is a sublevel. Okay, so this is a sublevel, and this is a sublevel. In the fourth principal energy level, same thing over here. Okay, this is a sublevel in the fourth principal energy level. The individual things on the inside, like this, that, those individual things are the orbitals. Okay, so there's the principal energy level, which is that coefficient out in front. There is the sublevel, which is the entirety of that shape. And then the individual orbitals within that sublevel. Okay, so like this sublevel has 1 orbital in it. This sublevel has 3 orbitals in it. And this entire energy level has a total of 4 orbitals in it. 1, 2, 3, 4. Okay, not a maximum of 4, it just has 4 that has electrons in it. Whew, that's a lot of vocab. All right, good news is, you guys, we can do a shorthand notation. All right, this is like a lot to write down. We don't have to write all of this stuff down every single time. We can do a shorthand notation. And the shorthand notation takes into account all of these electrons up to the valence electrons in that substance. So for like bromine has 7 valence electrons. They're in the 4s and in the 4p. Okay, those valence electrons determine the properties of that substance, right? The fact that bromine has 7 valence electrons gives us, a Lewis dot diagram that looks like this. Here I go, getting off track again, talking about extra stuff. And so we have to always show this end of the configuration, the total number of valence electrons that the element has. But all this stuff that comes before it, we don't have to show. In other words, you just go to the noble gas that comes before the element. Go to the noble gas before that element on the periodic table. And so before bromine is argon. I should have just known that off the top of my head, but it's late at night. And so that takes care of the 1s2, the 2s2, the 2p6, the 3s2, the 3p6, takes care of all of that. And all you have to write is what remains. 4s2, 3d10, 4p5. This is the noble gas or the shorthand notation. And again, the reason why we don't just write 4p5, we write everything that comes after the noble gas is because we want to be sure that we can show all of the valence electrons. Okay, so remember your valence electrons are the outermost highest energy electrons. They're the ones involved in bonding. They determine properties. They're very, very important to us. Okay, so all you have to do is look for the electrons in the orbitals with the largest principal quantum number, or energy level. Oops, I wanted to say number, and then I started writing energy level. Right? So here for bromine, highest principal quantum number, highest energy level is the 4th energy level. So there's 1, 2, and 5. That is 7 valence electrons. These 3d electrons, while they are a little farther from the nucleus, I'm sorry, they're not farther from the nucleus. They're closer to the nucleus than the 4s. But the 3d is actually a little bit higher energy than the 4s. That's why it's written in this way as opposed to the 3d being over here. Okay, so the 4s is a little bit lower energy. So there's some exceptions here with your d and your f electrons. But all you have to do, look for that highest principal quantum number, count up your electrons, that's your valence electrons. Or you guys just look at group number. Right? Oh, one last thing before we talk quantum numbers. Oh my God, have I been talking for over an hour? Probably have. Can we do an electron configuration for an ion? Ions. Remember ions gain or lose electrons, right? They gain or lose their valence electrons. So if you gain electrons, you are an anion, you are negatively charged. If you lose electrons, you have become a cation, you are positively charged. Just take away or give electrons in that valence shell. So like let's say we were doing the electron configuration for sodium. 1s2, 2s2, 2p6, 3s1. I thought maybe I needed to go to the 4th energy level, but that was potassium. Duh. Okay, so sodium, we all know, becomes sodium 1 plus. How? By losing its 1 valence electron. So if this valence electron goes away, this 3s orbital is now empty. The electron configuration is now 1s2, 2s2, 2p6, and that's it. Guess what this has the same electron configuration as now? Which is called isoelectronic. Means same electron configuration as the noble gas that comes before it. Neon. It's not neon, it has a different number of protons, but it now has the same electron configuration as neon, which is what makes it stable, which is why sodium wants to lose its 1 valence electron, right? You know all this stuff, you guys. Let's do another one. Let's do oxygen. 1s2, 2s2, 2p4. This is oxygen's electron configuration. If it were to gain 2 electrons, where would they go? Bloop. They would go into that 2p. 1s2, 2s2, 2p6. Guess what? Oxygen 2 minus is also isoelectronic with neon. Even though these ions are totally different numbers of protons, different behaviors, different charges, they have the same electron configuration as neon because everything wants to be stable with a full valence shell of 8 valence electrons. Oh my gosh, so much chemistry here, right? Now, valence shells are full with 8 except for that first energy level. That first energy level, of course, is full with just 2. All right. This is it, you guys. One last little thing. Quantum numbers. All right. Quantum numbers are just a way of representing or like tagging one particular electron. Okay, so this is a method for addressing each electron in the sequence. So if I wanted to like tag one particular electron in the sequence, I could do it with 4 quantum numbers. No 2 electrons will have the same 4 quantum numbers. The first quantum number, if you remember, is N. This is our energy level. It corresponds to the period on the periodic table, as well as the size of the orbital. And you'll recall our possible values for N are 1, 2, 3, 4, 5, 6, and 7. On, and on. It can actually keep going, right? We can excite electrons into higher and higher energy levels until that electron is ejected from the atom. But our possible ground state electron energy levels would be 1 through 7. Next is our angular momentum quantum number L. This represents the shape of the orbital. We also call this, remember, the sub-level. And it corresponds to the blocks on the periodic table, as opposed to the periods on the periodic table. So I was talking about S, P, D, and F blocks. Your possible values for L, well, let's start with the shapes, right? The shapes are S, P, D, and F. But we call these quantum numbers, so we just give a number code for L. S's are 0s, P's are 1, D's are 2, and F's have an L of, oh my God, I just wrote F's have an L of F. F's have an L of 3. This will all make sense. Hopefully it already makes sense because we did this last year, which is why I'm trying to go fast. This will make more sense when we do it for one particular electron. Next is our magnetic quantum number, M sub L. This tells us the orientation of the particular orbital that we are in. So for example, if we have an S orbital, like for example, the 1s, there's only one orientation. Like there's no like X, Y, and Z orbital for this guy. So we just call it a 0. But for P's, where we have 3, 1, 2, 3. Oh, that's making it look like these are in order because I wrote like 1s. Let's do 2. Right, so the 2s, we call this orbital a 0 orientation because that's the only orientation. But if we're doing a P, if we want to tag these individual orbitals within this 2p sublevel, we would tag it with a number line. So we put the 0 in the middle, and we call this orbital -1, and we call this orbital +1 to represent the X, the Y, and the Z orientations. So if we wanted to do a D, that's 5 of them, 1, 2, 3, 4, 5. So that would be 0, 1, 2, -1, -2. And then for F's, oh, I've run out of room. 1, 2, 3, 4, 5, 6, 7. F's are going to go up to 3, +3 and -3. Okay, I guess I should have had positive signs. You get the idea. So these possible values for M sub L, they can actually go from negative L to positive L. I know that sounds weird, but think about it. If you're in a P sublevel, the L for a P sublevel, the L is 1, right? Look over here. L is 1. I mean, P is 1. Well, yeah, fine. A P sublevel has an L of 1. Okay, so notice our possible values for M sub L go from negative 1 to positive 1. And if you have a D, you have an L of 2, so the D's can go from negative 2 to positive 2. Okay, so you just like make a number line. And then lastly is M sub S, which represents the electron spin. Okay, that means either clockwise or counterclockwise spin on those electrons. And we give an upspin electron a positive 1/2 and a downspin electron a negative 1/2 for our M sub S's. Okay, so let's go back up to my orbital diagram up here. Let's pick an electron. All right, I'm going to circle an electron in bright green. Let's take this electron right here that I just circled, and let's give it all of its quantum numbers. N, oh, you know, that is like not a great color. You can't really see it, can you? Oh no, did I just erase something from down here? Yeah, I did. Okay. I've just been terrible at picking colors lately. All right, let's do this blue here. There we go. All right. What energy level is that electron in? Well, there's a 3 out front. There it is. It's in the 3rd energy level. L, what shape orbital is it in? It's in a D-shaped orbital. And remember, D's we tag with a 2. Which of these D orbitals is it in, right? So it's like, this is my whole sublevel. There's 5 different orbitals to choose from. So we number line them to represent which of those crazy D shapes are we talking about here. So our M sub L is negative 1. And our M sub S is our spin, and that's a down spin, so a negative 1/2. There you go. Quantum numbers. Energy level, shape, orientation of orbital, and spin of the electron. Oy. That's it. We made it. I think that's all I have to talk about. Good job, you guys. We'll do a ton of practice in class. So I know that was a long lecture, but hopefully it was all review. And I will see you in class to practice. Bye-bye.